Now that we've talked about the equal sign, we're ready to take a look at equations as a whole, and particularly thinking about equations as representations of problem situations. Here you see the first grade standards that refer to equations. Keep in mind that we're in the operations and algebraic thinking domain. Children's work with equations should foster not only their facility with operations, but should also prepare them to think algebraically. Equations, equalities, and eventually inequalities play a big role in algebraic thinking, and so we need to ensure a strong foundation at the very point where equations enter into the curriculum. Although kindergarten children should have been exposed to extensive teacher modeling of equations, they were not required to use them as representations for themselves. In this lesson, we address the fundamental issue that underlies all of these standards, and that is understanding equations as a tool for representing mathematical situations and relationships. We will then take that a step further and look at how understanding equations as a representation provides direct benefits in solving for unknowns. Because we're examining equations from a conceptual perspective, which is necessary before children can develop the flexible procedural skills they will need with equations, it is necessary to follow a developmental pathway that allows children to first use concrete representations and then to use those concrete representations that they've already made sense of to stretch their thinking a bit further, first to diagrams as representations and then to equations as abstract and symbolic representations. To become proficient in writing equations, children need a prolonged modeling period. This isn't to say that they are not doing any writing of equations during this time, but there is limited to no attempt at formal assessment, the kind that shows up on grades, during this extended training period. They need time to see it modeled, to practice, to get feedback without feeling that they are bad at it. They're growing at it. Children are encouraged to solve problems using concrete materials as needed first, and then with teacher guidance, they can revisit those concrete actions and incrementally abstract those actions, first with a diagram and then with an equation. During this modeling period, a variety of problem situations and types needs to be used so that children develop deeper and more flexible understandings of equations. If they only experience equation writing for the easiest problem types, like result unknown problems, they are unlikely to develop expertise in equation writing. You will see as we go through this lesson that the ideas cannot be developed in a single lesson or even a single unit, but they are ideas that are built over time and revisited over the course of the year. Your modeling will be crucial in this process, and it's especially important in light of the previous lesson that you attend to the way in which the equal sign is being used in your modeling. I've shown here 6 different action problems which describe the exact same situation, but they differ according to the type of action and the position of the unknown. Because they're all action problems, however, they can all be represented using the format at the top of the slide. You begin with your start quantity, choose your plus sign or minus sign based on the kind of action, record the change quantity, and then the result of this action equals or is the same as your final quantity. Now, I'm not suggesting that you give this as a formula to children for fear that they will just stop thinking and try plugging and chugging. This will be a problem when they encounter non-action problems. Plug and chug is generally not helpful. I primarily offer this format to you here so that you can be aware in your modeling of things that you can attend to and verbalize as you're modeling. So, for example, let's take the last problem on the left. I had some marbles. Class, do I know how many marbles I started with? No? Okay, I'm going to use a question mark to communicate that I do not know how many marbles I'm starting with. Then Jenny gave me 2 more marbles. So what happened? She gave me more marbles? Should I use a plus sign if she's giving me more for my set, or should I use the minus sign? Involve them in the process as you build it. So you yourself are using that template to help guide your dialogue, not as a, here's a tool to just plug in 2 kids. All right? And you can use that to show how what you end up with as far as a situation equation for that would look like question mark plus 2 equals 8. And that's called a situation equation. It's an equation that exactly models the problem. It's also sometimes called a semantic equation. Keep in mind that these understandings typically begin with concrete experiences in order for the child to have already made sense of the question and the quantities, and at least have a working understanding of how those quantities were related because of acting it out. Now, their understanding of those relationships may be somewhat tacit and idiosyncratic, like they're just relating it to this problem. They haven't abstracted how other problems could be similarly structured. So before going straight into the abstract equation, I find it helpful to map out the relationships. You'll see in a few minutes why that's so useful. And I particularly like the number bond because it's very straightforward, clear map of the quantities that are involved. So it can be a useful tool. Here you see two of the problems from the previous slide, and the number bond is juxtaposed with images of our concrete experience so that we can then discuss the relationships. If we solved both of these problems in the same lesson, we might also have an interesting discussion about how they are similar and different, not merely superficially in terms of who the problem is about and what was the features like marbles, but also in terms of the quantities and how they're related, how are these number bonds similar and different, and our sets, number sets. You can use the concrete representation and the number bond to explore how the equation might be written. Here you see the concrete representations being shifted into a type of concrete equation. And here you see how the basic number relationship as mapped out in the number bond can be compared to the resulting situation equations. Children's understanding is deepened by making connections between the concrete and the diagram and the equation back to the concrete. Those connections are where learning and understanding is born. You can also occasionally revisit the idea of the equal sign and equality by using a balance or a visual tool such as this one to check out the relationship. I sometimes place an equal sign on a laminated card with a bit of sticky tape on the back so that students can decide if we can actually place it on the balance between the two quantities as shown here. So this image signifies that 2 plus 6 is balanced with, equal to, or the same as the quantity 8. The types of problems that we have discussed up to this point in the lesson are action problems. Another class of problems are the put-together, take-apart problems, and they also involve a total and 2 or more parts, so they can be modeled very similarly to the ones we've discussed thus far, although an operation sign based on an action is less likely. In the example problem shown here, there are 2 possible situation equations. You could write 8 minus 6 equals blank, or 6 plus blank equals 8. Both of these equations are mathematically acceptable for this situation, although one of them is a bit easier to solve than the other because it's already set up like a basic fact, 8 minus 6. Over time, as your learners are able to articulate how the format of a number bond is related to addition or subtraction, you might have them brainstorm math stories that they could tell for a given number bond. Especially encourage stories that do not involve a takeaway action after you already have one of those so that you can get a variety of equations on the board. So if somebody says takeaway, okay, let's do another story. This one shouldn't have takeaway, a different kind of model. And so then we can get different equations on the board, and when we do that, we can say, all of these are represented with the exact same number bond. So if I don't know how to solve 6 plus question mark equals 8, what could I try? Oh, it's the same as 8 minus 6. So in this case, you're laying the groundwork for how they're going to be able to do some conversions. Again, I'm sure you can tell by this, this is not a one lesson kind of a thing. This is an idea that gets revisited over time with many practical, specific, and varied examples from word problems for how it could be converted. And of course, different students will pick up on it at a different pace. If children are making sense of the equation, they should be able to draw a number bond, tell a story that fits the situation equation exactly, and then solve the equation. This is obviously not the sort of activity that you start with, at least not successfully, at the beginning of the school year, but it gives you an end-of-year goal to work towards and a quick benchmark for who still needs more modeling, and with small number sets, who's ready to be challenged by extending this into larger numbers and the more difficult, most complex problem types. I do want to caution you about two things as you model student work. One, don't use the word takeaway for the minus sign. Since so many subtraction word problems do not involve takeaway, it actually fosters misconceptions when children assume that subtraction and takeaway are synonymous. So we use the word minus or subtract for the sign when we read it out loud. Another issue to watch out for is how you're using the equal sign. When we record a child's mental math, we often use the mathematical equivalent of a run-on sentence to record the full thought process. Well, this is acceptable as long as we don't break any mathematical rules along the way. The version in red is breaking mathematical rules about the equal sign, so we want to avoid doing that. We can alternatively record their thinking in a series of equation steps, or we can use a similar run-on fashion, but don't use the equal sign. We can introduce a different symbol for gets me to. Children often really want a symbol for gets me to. This, I did this and it got me to this, and then I did that and it got me here. And if they don't have another symbol, sometimes they just, appropriate the equal sign to do the job for them, and that's a problem. So you might consider introducing a new symbol such as the arrow here for gets me to, and communicate to them how important it is to only use the equal sign when things on both sides are balanced or the same as. So that's an idea as well. Okay, now we're going to shift to how an understanding of these relationships that we've been talking about can actually support students as they find unknowns in equations. Finding the unknown does not merely refer to providing equations for the children that have unknowns and letting them do it. It's clear from standards 1 and 2 under the operations and algebraic thinking domain that children need to be able to do much more than that with equations. They need to be able to write equations that match situations and also subsequently solve those word problems. And standards 1 and 2 specify that the unknowns can be in any of the positions, which clearly makes writing and solving the equations more complex. To appreciate the cognitive difficulty in this expectation, consider the word problems here. If you took the Part A first grade module, you might remember our discussion of all the different problem types that first graders are expected to master. And you might remember that they vary considerably in structure and in difficulty level. Here you see 4 similar word problems, which are all different problem types. And the first one is the only one that makes sense for children who view subtraction as a takeaway situation. All of them are subtraction, but only one of these is takeaway. Although we discussed this in more detail in the previous Part A module, it is good to remind ourselves of the danger of calling that minus sign takeaway. I strongly suggest correcting children when they read it as takeaway by saying, let's read that as minus, or let's read that as subtract. Okay? For example, the first equation here would be read 7 minus 2 equals blank. That problem's pretty easy, as signified by the green E. The equation is easy to pull out of the word problem, and the equation is also easy to solve using either known facts or a level 1 or level 2 strategy. The remaining problems are more difficult, and you'll notice that oftentimes the action sign embedded in the problem is not the action sign that the actual operation you should use to solve. So the action sign may be plus, but the actual operation you need to find the missing value is subtract. So our discussion of finding the unknown from here on out primarily is going to center on what important concepts are necessary for children to develop the expertise they need to solve for unknowns in these bottom types of situations. The top one I think will come fairly easily, but where students are going to struggle is with some of these other types of problems. So we're not going to be discussing the kinds of equations you see in the first column here. Those are already set up in a format that are easy to solve. But we're going to look at the kinds of equations we see in the column to the right, and we're considering how can we help students take those kinds of equations and convert them to the kinds of equations that would be easy to solve, the kind that are on the left. The Common Core authors refer to this action of taking the situation equations that are awkward and converting them to a format that's easier. They actually call this developing an algebraic perspective, and it's listed in their progressions for first grade. Okay, so they're very clear, though, that concrete materials are where you start with this process. We're not teaching any subtract this from both sides of the equation. None of that stuff you remember from high school algebra. You begin with concrete, you explore the relationship, you then employ that relationship to help you decide how to convert the equation. And this is essential in building what the Common Core authors call a deep and flexible understanding of these building blocks of algebra on page 13 of the progressions. The difficulty of finding the unknown can actually be predicted by knowing the difficulty level of the problem type and then also determining whether the situation equation that results can be solved directly or if it's going to have to be converted. Most of the work that you do in building essential knowledge that allows them to convert equations should involve small number sets that children can easily manage. It's not going to take them forever to do a concrete experience. They have some number knowledge of these quantities. And it's really important then that you have dialogues that get them to articulate and map out the specific relationships and to get that out in the open where they can study it so that they can be thinking about the relationships and extrapolate from those relationships when the numbers get larger. In the Part A module, we discussed the relationship between addition and subtraction as per the second cluster under Operations in Algebraic Thinking domain. We spent more time on it there than we can really afford here, but understanding the relationship between addition and subtraction is just fundamental to converting situation equations to solution equations so that we can find an unknown. First, we need to understand that the three whole numbers in an additive relationship are essentially the same for both addition and subtraction. And I represent that same relationship with one diagram, the number bond. There is a total quantity which can be partitioned into two or more parts. Alternatively, in more kid-friendly language, we might call it the whole thing, which we can break into two smaller parts. Through many examples using specific and varied problem types, we can guide children towards noticing that the number bonds of all of the problems that end up doing addition have the same number bond, the same kind. That is, every time we ended up doing addition, we essentially have a number bond that looks like we know two parts and we don't know the whole. Likewise, they can come to see that for all the different kind of problem types where they ended up subtracting, they essentially ended up with a number bond where they knew the whole amount and one of the parts, but they didn't know the other part. This is so essential through classifying many different examples ending up with the same structure. They can begin to see what the underlying meaning is of addition and subtraction and how they're related to one another. Additional background knowledge to be fostered through many examples with specific and varied problem types would be the format of equations, with a particular reference to where the whole can be found. Sometimes children develop a misconception that the whole in addition is always found to the right of the equal sign, but you can see here that this is not the case. Also with subtraction, you'll want the children to recognize that the whole is always to the left of the minus sign, so that when they go to map a number bond, they know exactly where that whole can be found. Children often choose an operation based on a general action in a problem rather than on the mathematical relationships. In a recent research study that I conducted with first grade children, over 1/3 of the more than 100 children incorrectly chose subtraction for a problem that asked children to identify the total amount of lollipops given away if 7 were given away before lunch and 2 were given away after lunch. The work that you do towards understanding the mathematical relationships embedded in the words starts by acting out situations and then mapping out these relationships in diagrams so that they can be studied. Doing so allows for a long-term learning pathway that continually guides children towards deeper and deeper understandings of both addition and subtraction, as well as the relationship between these two operations. This understanding is necessary in order to effectively and independently solve all the problem types and to convert the situation equations that occur to solution equations as needed. I don't recommend introducing these ideas cold, but after you've spent some days solving problems and subsequently making number bonds and including the number bonds on two lists, let's put the number bonds that ended up with addition on this list and the subtraction on the other list. After you've done that for a while, you can ask students to look at your chart that you've made and to make some conclusions about it. What do we notice about all of the different situations where we ended up adding? And they can begin to articulate for themselves the two ideas that you see here, and which I've already described. Initially, these understandings are built through many situational examples that children have experienced, first through concrete by acting it out, and then to diagrams such as the number bond, and finally to a solution equation. Eventually, when they have a chance to build the core understanding of addition and subtraction, they should be able to apply this to any unknown add-end equation, like the one with no word problem associated with it. So here I just give them an equation. They should be able to put sort of general words to it, as you see here, and be able to picture the number bond that would be represented, and then be able to solve it using a level 2 or 1 or 2 method, or maybe even a recalled fact. This example is a little harder because essentially they have to get past that whole subtraction is not takeaway thing, but as a partitioning into two groups where one part size is unknown and where they can begin to see that this subtraction means that you're looking for a number which can be separated into an 8 and an 11. And when they recognize that that question mark is in the position of the whole, then they can begin to see that that would be the relationship. Children in your class who persist in using the term takeaway are going to really have trouble with this particular situation, which is a start unknown. You will notice that this lesson that we've just experienced here today did not incorporate any easy, quick fix ways to get your children to find the unknown. In fact, it probably seems like this is the hard way to go about things, but it takes a long time to build the depth of knowledge that is required in the Common Core. It will almost certainly involve some confusion along the way that has to be resolved, but it is possible to build this knowledge starting with small number sets that children are expected to bring to fluency, and then their understandings that they build with these small number sets and the relationships embedded in them will help them understand addition, subtraction, and the relationship between them more deeply, and that work can then be reinforced and extended to larger numbers when they